Welcome everyone to today's webinar on soil moisture, co-organized and co-hosted by NOAA's National Integrated Drought Information System, or NIDIS, and the National Weather Service. My name is Marina Skumanich, and I am a program specialist at NIDIS, coordinating the National Soil Moisture Initiative. I will be moderating this webinar along with my colleague Maggie Hurwitz, who is a hydroclimate services lead for the National Weather Service. A brief background on NIDIS. Next slide, please. NIDIS's mission is to work in collaboration with partners at all levels to help the nation prepare for, mitigate, and respond to the effects of drought. We do this through a series of activities, including the support of regional drought early warning systems, which you can see here on the map, and through work to improve drought predictions and forecasting, and to support effective drought planning and preparedness. In addition, NIDIS hosts the U.S. Drought Portal at drought.gov, a one-stop shop for information on drought, including the key indicator of soil moisture. Next slide. The National Weather Service is the NOAA office tasked with providing weather forecasts, warnings of hazardous weather, and other weather-related products to the public for the purposes of protection, safety, and general information. The Weather Service has weather forecast offices in communities across the U.S. and territories, supported by regional and national research centers. And I want to take a quick shout out to the forecast office staff on this webinar. Thank you so much for your service. Local weather forecasts and a wide range of other weather-related information can be found at weather.gov. Next slide. This webinar is also sponsored by the National Coordinated Soil Moisture Monitoring Network, a NIDIS-led multi-agency initiative to deliver a coordinated, high-quality, nationwide soil moisture information system to support the public good. The initiative is focused on two complementary activities: building a network of data networks from across the country, and building a network of people, that is, a community of practice around the soil moisture data provision, tool development, and applications. We'll put a link in the chat box for more information on this initiative. Next slide. Today's webinar is the first of a two-part webinar series focused on soil moisture. We're intending this series to help National Weather Service operational forecasters, other weather and climate service providers, and all other attendees to better understand soil moisture monitoring and its application to climate and weather monitoring. The goals of the series are to raise awareness of soil moisture as a key hydrologic indicator, review what we call the three-legged stool, the three key sources of soil moisture information that collectively provide a stable platform for understanding soil moisture conditions, and finally, we want to highlight practical applications of soil moisture data. This first webinar, Soil Moisture 101, will provide an overview of what exactly soil moisture monitoring is and the introductions to each of the three key measurement techniques: in situ ground-based systems, satellite retrievals, and land surface model outputs. The second webinar, held on March 29th, will feature presentations from climate service professionals on how they use soil moisture information to inform their decision-making. We'll put a link in the chat for that webinar. Both of these webinars will be recorded, and a link for the recordings will be shared with you by email and available through drought.gov. Next slide. A quick overview of our agenda today. We will take about 30 minutes to play the recorded presentations as listed below, starting with an overview of soil moisture monitoring and then turning to each of the measurement techniques. All of the presenters are here with us today and are available to respond to questions that you type into the question box. So please do add your questions as they come up, and we'll address them after all the presentations. After the presentations, we'll go hold a panel discussion. We will first provide each of the presenters a brief opportunity to add any further comments to complement their presentations, and then turn to a Q&A. We will now turn to
Marina, I have access, so I'm going to play the presentations.
Okay, we will now turn to our first overview presentation by Mike Kosh with USDA.
Hello, my name is Mike Kosh, and I'm with the USDA. I'm here to talk about how soil moisture affects your everyday life. When we talk about soil moisture, we must give a definition first. Volumetric soil moisture is volume of water per volume of soil. This is the common usage that most of our measurements are trying to get at, this ratio of volume of water to volume of soil. But there's an absolute way to take this measurement, which is going out and taking a physical sample. We use the thermographic metric method, which would be shoveling out a volume of soil into a can or a tin or a bag, then taking that sample to a laboratory. We put that soil, we'd weigh it, we'd put it into an oven. That oven would run for 24 hours and it would give us just the soil back, removing all that water over the day. And then we would know the difference between soil and water and soil. Then we know the water. And that ratio is really what we're talking about here. Volumetric soil moisture. Seems very simple, but it's pretty complex. And it takes a long time. So if we really want to get at this from other means, like remote sensing or modeling or regular in situ monitoring. Before we go too far, let's talk about how we actually measure soil moisture. Here is a typical probe that you would see installed in an in situ network, one of our 3 legs. This is inserted into the sidewall of a hole that we dig, and it measures the dielectric constant of the medium in which it's installed. That medium, for our purposes, is a mixture of soil and water. Water has a very high dielectric constant, soil generally has very low dielectric constant. Therefore, the higher the dielectric, the more moisture. We can typically have a good observation range of moisture which goes from 0 to 50% moisture. 50% moisture is in the range of a muddy walk to work, for instance. So this can monitor automated at low electrical cost. Solar panels generally are enough to run these things. And it gives a small volume of measurement. And we hope that this installation provides a good reference point to the large area around it. So when we talk about soil moisture stations in situ, in place, this is really what we're referring to, something along these lines as an example. Now you know how it's monitored via in situ. But we have other ways of measuring it, including remote sensing from aircraft and satellites. Or if we have a lot of other information, we can model. And that really comes from trying to get at the entire water cycle. But why do we need to measure soil moisture anyway? Soil moisture is a valuable parameter for a variety of uses, including agricultural management, where we would use water, soil moisture estimates to help us irrigate effectively. We don't want to over-irrigate, we don't want to under-irrigate, we don't want to have a drought. We don't want to have water run off all of our valuable nutrients into the rivers. We also want to be able to plan. Our river forecast centers need soil moisture estimates so that they can control releases from reservoirs as rain patterns come through. Because the more water you have at the surface, the more will run off. And this is used in a variety of conditions for basin management. It's also used for assessing the risk of wildfires. Knowing the amount of soil moisture available at the surface basically tells you how much water you have in the plants. And then you know what kind of fuel load you have. And knowing the fuel load can tell you your risk for wildfires and forest fires. These things are all affected by soil moisture in their largest scheme of things. But we all start with a simple measurement. We need to know what is the soil moisture. One of the older methods of doing this is to actually have a physical station monitoring soil moisture, say, down the road at your local college at the airport. Here's an example of a typical station at the Soil Climate Analysis Network. This is in Beltsville, Maryland, just down the street from my office. This station has been providing data for about 20 years, which is a valuable record of data that will both inform climate decisions and modeling development, as well as providing just simple reference for any of the research going on at this experimental station. We need to understand soil moisture state So we can start to get an idea of what the evaporation rate is, what the energy cycle is doing, because soil moisture also controls what the solar radiation does as it hits the surface. Does it turn that water into water vapor, and therefore taking that energy and putting it to evaporation instead of heating the soil? But here we start with a simple station. A couple of sensors in the ground, solar panels running everything, providing the basis for all of the research that can happen and all of the decisions that can be made off of understanding a few parameters at the surface. We're now going to talk about how networks like this across the nation could be coordinated together to better understand the water cycle, energy cycle, and carbon cycles of the US and make better decisions in the future.
Okay, I see some folks are having audio connection problems. Our apologies. It's hard to know if that's a platform, webinar platform issue or your own link in. We do have these videos on the web, and we can provide links through as they go forward. But again, apologies if you can't get your audio to work. So we will now turn to Chris Fiebrick's presentation on in situ networks.
Hi, I'm Chris Fiebrick, and I'm going to talk a little bit about soil moisture data and products from an in situ perspective, and more about how mesonettes around the nation measure soil moisture with some specific examples from the Oklahoma mesonet. To start off with a little bit of background about the Oklahoma mesonet, we are jointly operated by Oklahoma State University and the University of Oklahoma. And the reason I thought it might be important to point this out is because it's similar to a lot of the statewide and regional networks across the US. Not all of them, but most of them are operated by universities. This is the layout of our sites across the Oklahoma mesonet. We're spaced about every 19 miles, which is approximately on the mesoscale. It's a scale that allows us to detect medium-sized weather events, for instance, fronts and outflow boundaries and things like that. About half of our mesonet sites are on privately owned land, where a landowner has allowed us to put the site on their property, and the other half are on publicly available land. This is what a typical mesonet station looks like. They're oftentimes a 10-meter tower. Reason for the 10 meters is so that we can put the wind speed and direction up at the top of the tower. 10 meters is the official WMO height for wind speed and direction around the world. And then along the tower, other measurements: air temperature, relative humidity, pressure, solar radiation, rainfall, and then the soil temperature and soil moisture measurements also. Now, with the various mesonets around the US, there are a lot of different brands of sensors used. This is showing just a sample of the various sensors. There are manufacturers like Campbell Scientific, Hydroprobe, Aclima, ThetaProbe, and others. These are just some examples. Not only are there different brands of sensors, there's also a couple different soil moisture parameters that are used amongst the various networks. So when we talk about soil moisture, it could mean matrix potential or volumetric water or fractional water index or even plant available water. So it's important to understand the differences between these various soil moisture parameters that are measured. And a little bit more on the layout of mesonets across the US. This is a map from the National Mesonet Program to show you that we have a great coverage of statewide and regional mesonets across the US. Now, not all of these mesonets record soil moisture data, but many of them do. And I believe most all of them are working towards making soil moisture measurements in their networks. There's a lot of value, as you can imagine, to having the soil moisture data co-located with the other measurements from a mesonet tower like rainfall, relative humidity, temperature, and estimates of evapotranspiration. One of the things that we strive for as mesonets across the US to try to set us apart is our emphasis on data quality and reliability and completeness. So we do a lot of work with calibrations, quality assurance, and we want to be able to deliver services in near real time. So there are a number of other measurements being made, for instance, by field experiments or research projects and the like, and those are of course very valuable. But as mesonets, we want to have that real-time, complete data flowing in order to document climatic conditions over the long term. So to give you an example of some of the products we have in the Oklahoma Mesonet, this first one is fractional water index, and it's derived from our matrix potential measurements. And fractional water index essentially goes from 0, which is wilting point for the plant, up to 1, which is field capacity, meaning that the plant has unlimited access to water. And so we make these products, update them throughout the day, indicating that fractional water index at 2 inches, 4 inches, 10 inches, and at 24 inches based on the sensors we have at those specific depths. We also create 7-day changes in fractional water index, which help us look at whether the state's moistening or drying, if drought is intensifying, and the like. And then graphs of the time series of the data also. Now, to convert that data into a product that maybe a grower or producer could use, we also generate plant available water data. And with these, we are integrating the observations over the 4-inch depth, 16-inch depth, and 32-inch depth. And that corresponds with some of the various plant depths, whether they're seedlings or shallow-rooted plants and deep-rooted plants. So in order to generate these estimates, we took soil cores. Oklahoma State University did the analysis with the water retention curves so that we could estimate how much water is in that profile. And so then we had this set of plant available water maps, again, integrating that 4-inch depth, 16-inch depth, and 32-inch depth. And then we also compare that to what the soil profile indicates would be the maximum water that integrated depth could hold. And we can create percent plant available water maps also. And then this is an example of the time series data. Our network takes soil moisture observations every 30 minutes, so we can plot those over the course of a day, weeks, months. And so what we've got plotted here is the 5 centimeter time series in red, the 25 centimeter in yellow, and the 60 centimeter in green. And we can see that with a half-inch rain event that happened last fall, it moistened the 5 and 25 centimeter depths. Those fractional water index values jumped up to close to 1, which is saturated. But then it took a 1 3/4 inch rain event before the 60 centimeter depth responded and was able to moisten and become saturated. One other note on this time series graph, this goes through into February, the big Arctic outbreak the southern Great Plains had, and temperatures well below freezing, which caused our soils to freeze at 5 centimeters. And because of that, our quality control removed those observations because the sensors didn't perform correctly when the soils were frozen. And then we do try to validate our estimates of soil moisture data. In this example, we looked at the state that was in at a period when it was in drought conditions. So it was somewhat of a controlled situation where all the soils were dry and we had a big rain event move in. And we then looked at how much the plant available water increased at each site compared to how much rain fell. So the 1-to-1 line would mean that 1 inch of rain fell and the plant available water increased by 1 inch. But of course, that's not necessarily the case. A lot of the data is below that 1-to-1 line, indicating that the rain that fell didn't necessarily all go into increasing the plant available water. Some of it ran off, some of it drained and infiltrated through the column, which makes sense. So all in all, these were some good findings to give us confidence in our estimates of plant available water. And then lastly, some limitations of soil moisture measurements from mesonettes. There's a lot of variability, of course. If it rained more at our mesonet site than it may have in your area or in your field, we'd get different soil moisture values. Also, our measurements in the Oklahoma mesonet are made under vegetated sod. So if your field is bare, that could change the infiltration and the soil moisture there. And then lastly, the soil structure could be different at our mesonet site and in your area. So those are some of the considerations to make when looking at mesoscale soil moisture observations. And I'm happy to take any questions during these sessions, or you can email me at febrick@ou.edu. Thank you.
Okay, Kristen will be here to take questions, but we're going to continue on with our next presentation, which is John Bolton's discussion of satellite retrieval, soil moisture information.
Hey everyone, this is John Bolton. I am a research scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland. And today I'm going to be discussing satellite-based remote sensing of soil moisture, and particularly how that can complement and leverage in situ-based observation of soil moisture that we will be discussing today during the listening sessions. So first I'd like to point out that this figure here, this is the Soil Moisture Active Passive Mission, or SMAP. This is NASA's latest and greatest achievement focused on satellite-based observations of soil moisture. This was launched in 2015. I'll go into this in a little bit more detail in a second. So NASA actually has quite a large number of Earth-observing satellites in our Earth fleet, as shown here. We have over 18 different satellites that are focused on different components of the water, energy, and carbon cycles. So traditionally we use radiation-based remote sensing technologies to sense different components of the Earth system. So we see here highlighted on this cartoon of the electromagnetic spectrum, we have soil moisture, snow, ice, rainfall, and vegetation. And the region identified as microwaves, this is the region of the electromagnetic spectrum that is sensitive to soil moisture. And in the next figure, I'll show you how that is done. So in soil moisture remote sensing, there's two main approaches for doing this. You have a passive approach and an active approach. Passive approach you can think of as your eyes capturing ambient light, so you can see. Active is similar to a radar gun, so it emits radiation and measures the backscatter or return. So the passive instrument, in fact, it's a microwave radiometer, is measuring the thermal emission from the land surface, and this is measured in brightness temperature. The soil moisture, in fact, is the dominant effect on that received signal in the absence of significant vegetation. On the other hand, the active component, or backscatter, or radar, is you have the ability of having a finer spatial resolution, and it's also sensitive to soil moisture. However, it's influenced more by vegetation and surface roughness. So the goal here is to try to combine these two technologies optimally, so you can leverage the capabilities of both. Now, the value of remote sensing based approaches is realized mostly in the fact that you have the capability of having a global perspective combined with frequent revisit times. Now, these satellites are flying at several hundred kilometers altitude, and they're going quite fast. So you have the potential for frequent revisit times, and you have a regional perspective of soil moisture. Now, what you can do with this, it provides an improved understanding of the hydrologic cycle. You can link the processes of the terrestrial water, energy, and carbon cycles, many different applications. But the key here is to have a long-term consistent data record at the highest possible temporal in spatial resolution so that you can strategically merge these with in situ observation networks. Now, satellite-based remote sensing is not going to replace in situ, and in situ is not going to replace satellite remote sensing. You have limitations with remote sensing-based approaches. You're limited by your penetration or sensing depth, as well as your revisit time is the highest is perhaps probably daily revisit time. Yet you have this spatial resolution and regional perspective combined with a global view of soil moisture, and this provides a lot of value when you're applying these. It's interesting to look at the evolution of satellite-based soil moisture remote sensing. Here on the left we see the SIMR satellites were first launched before 1980. And as technology has advanced, mostly our ability to capture longer microwave wavelengths, so as the fidelity and reliability of the remote sensing based soil moisture products. Most notably, the NASA Soil Moisture Active Passive mission was launched in June 2015. So as I just mentioned, NASA has a long legacy of microwave radar and radiometer instrument and algorithm design. On the top right figure here, you see a truck-mounted instrument. So these were done as a test bed for future satellite-based sensors. And the next figure down, this is a sort of a demonstration of a strategic blending of agronomic information and satellite data and models. So taking these satellite-based observations, merging them with in situ observations. So this can be done for calibrating and validating current and even planned satellite products, for increasing the fidelity of the in situ network as well as the satellite-based products. And this leads me to value-added products. So the key here is trying to strategically apply these, merge these with a land surface model or a crop growth model or a soil moisture model so that you can improve and constrain those models from frequent satellite observations. And from that, you're able to have more informed information, such as the Dynamic Agriculture and Productivity Index, or DAPI. That's a partnership with the National Agricultural Statistical Service and the Foreign Agricultural Service, as well as USDA's Crop Condition and Soil Moisture Analytics, or crop CASMA product. Now let's take a look at what SMAP is seeing. So the objective of the SMAP mission was to provide high resolution and frequent revisit global mappings of soil moisture and landscape freeze-thaw state. The mission target for accuracy was 4% soil moisture and a sensing depth of 0 to 5 centimeters. Now the repeat time of the SMAP sensor is 3 days, so you have a 3-day global coverage capability. And what this animation here is showing is precipitation memory. It's simply just the NASA GPM, or Global Precipitation Mission, observations of precip overlaid with the soil moisture active passive anomalies. And it's pretty cool, and it really captures this idea of precipitation memory. So NASA is also partnering with the Indian Space Agency for an exciting mission planned for launch in 2023. This is the NISAR soil moisture mission. And what's exciting about this, it will have a much higher resolution of 200 meters, but it will have a more infrequent global coverage of every 12 days. That said, we're very excited for this next horizon of satellite-based remote sensing. Now, as I mentioned before, the value of ground-based measurements is the high accuracy that you have. However, they suffer from sparse and limited coverage. Now, the key here is to combine these with a satellite-based observations. You can do this through combining with a land surface model through data assimilation. In fact, that's what we are showing right here. This is the NASA USDA Global Soil Moisture Data Assimilation System. And by doing this, you're able to constrain this, in this case, it's a 2-layer soil moisture model. So you have a value-added product that is also providing global coverage, and it leverages both in situ observations and satellite-based observations. Now, because the SMAP scatterometer stopped working in 2015, folks have been trying to figure out ways of combining different observations to meet that targeted higher spatial resolution that was aimed for with the SMAP mission concept. So what we see here is a demonstration of a finer spatial resolution product produced by Fang, Lakshmi, and others at the University of Virginia and USDA. And what they've done here is they've leveraged this concept of thermal inertia between the daily surface temperature changes and the averaged soil moisture over different vegetation conditions. And the way they did this was that they looked at these relationships over a long historical record using the North American and the global land data assimilation system, GLDAS and NLDAS, surface temperature and soil moisture, as well as observations from satellite, like the Advanced Very High Resolution Radiometer, AVHRR, as well as the MODIS, the Moderate Resolution Imaging Spectroradiometer. And what they were able to do here is produce essentially a MODIS and SMAT based higher resolution product that is leveraging the surface temperature observations. And here we see comparisons with the coarser SMAT based 9 kilometer product with the downscaled 1 kilometer and even 400 meter resolution soil moisture products. So this is being produced over CONUS as well as globally. Here's an example of a value-added product that is applying a spatial disaggregation algorithm. Here, this is the thermal hydraulic disaggregation of soil moisture, or TSIM approach, was used to provide 1 kilometer based spatial resolution observations. And what's neat about this is that it's provided in an interface that also provides agrometeorological conditions. And so this allows the partners at the National Agricultural Statistical Service to have quick and easy access to near real-time soil moisture observations, as well as crop conditions and soil conditions. So it's very helpful for assessing current and future crop productivity. And it's called Crop Chasma, and there's a link. You should check it out. It's pretty cool. So I hope this provided some context of satellite-based remote sensing and how it's related to and tied and depends really on in situ gauge observations of soil moisture. So there's many interesting applications of soil moisture that are coming about these days, whether it's constraining hydrologic weather models or informing agricultural monitoring or improving flood or drought forecasting. Right here, this is a pretty cool example of assessing fire risk through satellite-based observations. And it's pretty simple and very straightforward. On the top left, you see the time series of observed fire counts from satellite. And on the bottom, you see just a time series of lag correlation of soil moisture anomaly. Pretty straightforward, but also a wonderful demonstration of the value of soil moisture. So that's it for me. Thank you very much for your attention, and I look forward to these listening sessions.
Yeah, okay. You hear people presenters referring to listening sessions. We are using these presentations that were recorded for a series of listening sessions last summer, and we're hoping to do more of them. So if any of you are interested, just email me. I'll put my email in the chat, and we'll take that forward. But now we're turning to our last presentation on model outputs, which is actually done by me, Marina Skumanich. Hello, everybody. My name is Marina Skumanich. I'm the Soil Moisture Program Specialist for NIDIS. I'm going to be speaking very briefly today about modeled output soil moisture data and products, and then very briefly after that, a little bit about blended products. So what models are we talking about? Well, these are land surface models, or LSMs, you might hear of that, and they are our best representation of a complicated hydrologic system. So in these models, there are physical and statistical equations used, as you can see there on the right. Pretty complicated. If you can read that, you're in the club. And those equations are used to simulate the flow of water and energy between the land, vegetation in many cases, and atmosphere. And as part of these land surface models, there tend to be two components: the hydrological model that would be linked to atmospheric models to get that full circle of water movement. The water balance approach is what's focused on here. We are looking at the change in soil water storage that's a result of incoming fluxes such as precipitation minus outgoing fluxes. That would be evaporation, transpiration, movement to groundwater, etc. And there are just a very wide range of land surface models that can provide soil moisture data, ranging from very simple to very complex, based on a number of factors. One important one is the number of soil layers. In the case there on the right, you can see the NOAA MP schema has 4 soil layers. In addition, there's a question of the number of hydrologic components that might be included. For example, in terms of dynamics, is snow considered? And if so, how many layers? Is evapotranspiration considered? How is vegetation engagement with water factored in? There's a lot of complexity that can come from that. Even if that's all consistent from model to model, there are a lot of different assumptions about how to handle those dynamics and what kind of parameterization to use to support the model. In addition, different models have different geographic coverage. Obviously, some are CONUS only, and others go globally, etc. Some are just regional. And then there are different application targets. In some cases, modelers are building for research, and in other cases for operations, and that will affect the way they develop the model. Well, there are a number of model enhancements and extensions that are worth having just a sense of. One of them, atmospheric forcing, is quite standard at this point. This is the use of precipitation and other meteorological data as inputs to the land surface model. So this way the model doesn't run its own little box, but actually is bringing in actual meteorological conditions to help inform soil moisture and other data outputs. Similarly, and also quite important, is data assimilation. So that is the use of observational soil moisture and related data to course correct the model as it goes along. In this case, you would be running a model and also taking observational data and doing some comparison and some kind of blending of those two values to find sort of the truer actual soil moisture conditions. In addition, modelers sometimes run ensembles, and that could be either in the form of running the same model multiple times with the idea that through a series of runs, you might become closer to an actual true value or better estimation of the soil moisture value. In addition, there's the opportunity to run multiple models simultaneously, and this way you can take advantage of the fact that different models have different strengths and weaknesses, different areas they focus on, and you might find that the ensemble value of results is, again, more accurate than that which you get from any single model. And then taking that one step further, a number of organizations have developed integrated platforms, and so the North American Land Data Assimilation System, or NLDAS, and the variations there provide a series of models that can be run, a series of different data sets that can be assimilated, and other kinds of support packages for researchers. Another example is the NASA Land Information System, or LIS. So very briefly, here's a NASA SPORT-LIS model product, just one example. SPORT stands for the Short-Term Prediction Research and Transition Center at NASA, and it provides soil moisture on high-resolution grids for the CONUS, about 3 kilometers, in real time, updated every 6 hours, and it is based on the NOAA land surface model with input from the NLDAS2 atmospheric analyses, so that's using another land surface model package to provide atmospheric analyses, and then the MODIS satellite vegetation as an enhancement to control for vegetation effects. And it provides sub-country soil moisture conditions. A couple images of the output from that product. We've got on the left there the surface relative soil moisture or available water on July 9th, and then on the right there, root zone relative soil moisture on the same time. And this would allow you to compare a little bit of what's at the surface level, what sort of immediate, more recent effects of precipitation, for example, etc., versus on the right, sort of the longer term status of the soil column. Like any tool, modeling for soil moisture has certain advantages and some limitations. In terms of advantages, modeling complements in situ data observation because we can't have sensors every kilometer. It provides continuous spatial and temporal resolution, and with that, higher resolutions, in many cases a kilometer or less. With increasing computing power, we'll be able to get more and better outputs from the models, and models allow us to do what-ifs or other types of exploration. At the same time, there are some limitations to modeling. The most basic being that a model is just a simplified version of reality. So there you go on the right, you can see our leaky bucket providing our hydrologic cycle. Of course, modelers are making their models more comprehensive and more complex over time, but complexity brings its own issues in terms of the kinds of bias and error correction that's needed. There's still a question about the quality of forcing data for models. The atmosphere is very complicated, and our ability to really understand atmospheric dynamics is still unlimited. And then in some cases, modeling systems have latency. As the modelers are checking outputs for quality control, quality assurance, that will delay how quickly we can get model results. So that's a quick overview of modeled soil moisture data and products. And just to finish to talk briefly about blended soil moisture data and products, which would blend all three legs of our stool to provide our soil moisture information system. As you can probably infer from what I've talked about, there's already some overlap in products. Well, our modeled output is using data assimilation and other techniques to bring in observational data. And in addition, remote sense data, in many cases, satellite outputs are fed to models to smooth, etc. So the question for us is, how can we be more intentional about this process? That is one of the objectives of our initiative, to build these blended products that really takes advantage of each leg of our stool. Well, that ends my presentation. Thank you very much. Okay. Thank you, everybody. That does end the series of recorded presentations. Again, our apologies for those of you who have had audio or other difficulties. We will be doing a post-event review, and hoping we can work with the developers and get a little more stable platform. We also are recording this, and so if you have struggled to hear, we will be able to share that recording, which should be fully functional, so to speak. So we are going to now turn to our panel discussion, and I'd like to invite the other fellow presenters to join us. And I'm going to turn over the moderating now to Maggie Hurwitz.
Thank you all for your great presentations, and I just wanted to first invite all of you and our additional subject matter experts to add anything to the presentation, the recorded presentations that were shown.
I actually did have something to add, and I'm hoping several of you in the audience are asking this question. Maybe you've got it posted in the question list, which is, what about the National Water Model? You know, that is something that NOAA is really putting a lot of emphasis on. It is a state-of-the-art land surface model that to do hydrological forecasting, monitoring and forecasting. It is currently not considered operational in the soil moisture side of things. They are wanting to do a better job of some of the layers, and so that is something that they're saying they'd like to be more orienting people to wait till the next version, which I think is either next year or the year after. So, but just to mention, that is in the pipeline and will become another resource for us.
Thanks, Marina. Does anyone else have anything to add to their recordings? If not, there were a few questions from the audience asking questions about the horizontal and vertical resolution of the soil moisture data sets, as well as the length of the data record for the various products that you presented. So I'm wondering, for each of the in situ and remote sensing and modeling experts here, if you could just review kind of the main products that you shared and what the resolution and data length is for each of those, that would be great.
Chris, you want to go first?
Sure. Thank you, Mike. Yeah, so in Oklahoma, we have sensors at 5 centimeters, 10 centimeters, 25 centimeters, and 60 centimeters. For the first, and these records go back to about 1996. In those early days, we also had a 75 centimeter depth, that we found too difficult for us to maintain and reach down that far over time. So we decommissioned that, but the 5, 10, 25, and 60 basically go back to 1996.
John, do you want to talk about the satellites, their history?
Yeah, can you hear me?
Yes, we can.
Yay. Okay, cool. Hey, this is John Bolton from NASA. Yeah, so thanks, Maggie. That's a good question. Well, I'll address SMAP first and foremost. I think that's probably the primary satellite-based instrument that people are interested in. So SMAP has a few level 3 products and level 4. Level 4 is the satellite-based observations that have been merged with the NASA land surface model, catchment model. So what you're providing there is a surface and root zone. So essentially, what you can safely say that the sensing depth is roughly 1 to 5 centimeters. That's what we typically say for SMAP. But with the level 4, you actually have root zone included. And as far as the spatial resolution, there is a 39 kilometer resolution product. There's a 9 kilometer resolution product in the level 3 and level 4, and now there's an additional 1 kilometer global product, which I showed a little glimpse of as well. The crop chasma, of course, that is only over CONUS. That is also providing a 1 kilometer spatial resolution. Go ahead.
Wait, no. Okay. So starting remote sensing of soil moisture in the C or X or L bands started in about 2002 with the AMSR-E instrument on board the Aqua satellite. Anything that's C band is going to run just a 0 to 1 centimeter. It's very superficial, and anything with too much vegetation is not going to be accurate. You need to go to the L band, which is that 0 to 5 centimeter depth. And as John described, there are products that provide more of a full root zone 0 to 1 meter estimate. That is a model taking in the data that they collect from the surface and then modeling it down. The networks, Chris described his, there are matrix potential networks, there are soil moisture sensing networks. Most of them start, I think Chris is one of the oldest. Illinois also has a very old network into the 90s. National networks started in like 2002, maybe 2007, some of the more national-based networks. They all try to get more in the surface, 5, 10, 20, 50 centimeters, and if you're lucky, 100 centimeter depth. Most of the dynamic range is occurring at the near surface where any amount of rain is going to have a signal there, but it's very hard to see a dynamic response down at 1 meter usually. And most of your models will run as far back as the data works to help train them. So you're looking at models that maybe there's a 20-year record. You can then theoretically go back in time if you have the other components of that model suite of data like precip. So hopefully that answers the questions. The monitoring sensing depth of the sensing depths, but then the spatial range of most of those sensors is going to be pretty small unless you're talking about the Cosmos network, which is more of a couple hundred meters in scale. And John covered the active passive. The passive is what we have working mostly. The newer sensors that are active will have a much higher resolution down to sub-kilometer, but they will be a little bit less accurate. But sometimes if you just need spatial patterns, that might be enough. I'm done.
Hey, Marina, did you want me to talk briefly about the land information system then? Okay.
Yeah, we want the big guns on now.
Yeah. Okay. So at the Short-Term Prediction Research and Transition Center, or SPORT, we've been managing a land information system run using the legacy NOAA model. And our database goes back to 1981 for the climatology, and then we derive percentiles off of the 33-year climatology in near real time for the assessing, anomalies relative to the 33-year climatology, and that's across the CONUS domain. We also run the model at approximately 3 kilometer resolution, 0.03 degrees. And you could consider it a value-added level 4 product, similar to what was described about the value-added catchment that was run. We do not do a data assimilation on the official SPORT-LIS product, but we do have a parallel run that has been assimilating SMAP retrievals since the beginning of SMAP in 2015.
Thanks, Paul. Any more comments on the kind of overview of the characteristics of the data set? If not, I'll turn to a few more of the questions from our audience. So I'll try to mix, provide a mix of the kind of data types. So the first question is about whether measuring soil moisture accounts for the cone of depression around a well or other anthropogenic water diversion. So I guess that's for in situ measurements.
I can speak for in Oklahoma. We try to avoid those types of anthropogenic sources around the sites when we're siting the locations. We have had 1 or 2 instances where we've had lateral flow from a drainage ditch that we could detect because a deeper depth would moisten before a shallower depth. So we have some QA processes that help us try to identify those. You know, in general, we're trying to watch that the precipitation events moisten the shallower depths, and then it infiltrates and gets recorded at deeper and deeper depths. And then the drying happens in reverse. And so we do have some ways to try to detect those things, but I'm sure there are cases where that, you know, siting of a station could be influenced by those.
And some networks are put out short term to actually monitor anthropogenic effects, including irrigation. So we try and understand what is being measured and what's its purpose. Oklahoma Meson is trying to understand the natural landscape, and certainly don't want to be under an irrigation rig. But if a farming initiative is putting out a network to control their irrigation, they're going to have it under their drops and try and plan accordingly.
Thank you. So along the same lines, there's a question about more anthropogenic activities like drilling into aquifers, mining activities, and so forth. So is that incorporated into the models that you mentioned?
I guess I'll try to address that one. So the main activity I think that would affect the soil moisture in models would be the irrigation and you know, widespread irrigation in farmlands, and that's not presently incorporated into our product, but there are parameterization schemes in order to account for approximating soil wetting through irrigation in models. And there's been some inferences in that soil moisture data assimilation, at least if the irrigation footprint is widespread enough that that wetting footprint could be incorporated into the model through data assimilation from what the satellite sees.
Okay, thank you. So turning back to the in situ measurements, there's an interesting question about basically maintenance of the instruments and how often do they need to be visited by technicians, and I guess how often do they break? And I also wonder, you know, given the pandemic in the last couple of years, has there been an impact of our ability to maintain all of these observing sites? So I suppose that's more for Chris and Mike.
Yeah, I'll talk before Mike. The soil moisture sensors are definitely more problematic since they are in the soil compared to the atmospheric sensors. There's a lot more that can go wrong in the soil with, you know, soil cracking and rodent damage and just the harsher conditions in the soil compared to a temperature sensor that's maybe in an aspirated housing or something like that. So we do have quite a few problems that occur, and it's going to probably depend on the age of the sensor. But we do have some of our soil moisture sensors that have been out ever since they were installed. We treat them differently than our other atmospheric sensors. Our atmospheric sensors, we actually rotate on an interval so that we're repeatedly refreshing them and calibrating them. Whereas the soil moisture sensors, it's better once they're healed into the soil to leave them where they are rather than to disturb them and pull them out and reinstall them. So there are considerations that need to be made for maintenance for sure with soil moisture sensors. And Mike has a lot of experience looking at this too.
Yeah, so your state mesonettes that everybody can drive, not easily sometimes, to all of the stations probably would hopefully get monthly or at least bi-monthly maintenance. The more problematic sensors would be like the precip gauge, for instance, or air temp, solar radiation sensors, things like that. The national networks where you have to fly there certainly were impeded by the pandemic. Some local maintenance could happen by people that knew what they were doing. They were more on an annual, biannual, 3-year cycle. And most networks, probably the worst a network gets, if it's still an operational network, is maybe 20% failure rate. 20% of the sensors aren't reporting something at some time. Usually it's this station's bad, that station's bad, and they've just been bad for a while until they can get out there and fix it. And it's been problematic, but one of the goals is to promote and improve the maintenance and funding of these networks so that we have better maintenance records and improve that 80% operational, and also provide the value. A lot of the climatology value comes from longer straight records of data. So that's our goal.
Great answers, thank you. And so the last question for John Bolton, if he's still there, how does snow cover affect the remote sensing of soil moisture?
Hey, sorry, Maggie, was the question about snowpack?
Yeah, how does snow cover, snowpack affect the remote sensing of soil moisture?
Ah, that's a good question. So there's actually a product called the soil water equivalent, also known as SWE, S-W-E, because the snow, the microwaves are sensitive to essentially to water, and they're sensitive to the water in plants. They're insensitive to the water in the soil as well. And so what is done through these algorithms is trying to characterize that the physical nature of the water on top of the soil surface, including snow as well. But this is an additional product that is provided through the SMAP product as well, sort of a freeze-thaw product as well as the soil moisture mount.
Great, thank you. So we can't get to all of the questions, but hopefully we've provided a nice cross-section today. So back to you, Marina.
Great, so we are at the top of the hour, and so we'll be ending this webinar, but I just want to mention, as I put in the chat, we have got all the questions many of you have submitted recorded, and if we didn't get to your question, we will be asking our panelists just to do a brief response, and so we will include those answers along with the link to the recording and the individual YouTube connections again as well, sending that to all of you. So thank you very much for joining. Really appreciate your time. Hope this was informative, and please fill out the survey as you leave. Thank you. It'll help us do a better job the next time. And thanks to our panelists for all your great work.
Thank you, Marina.
Thank you, Marina.
Thanks.
Thanks, Brenda.